Today, we're tackling a problem that challenges us to identify the weakest rows in a matrix. The catch? Weakness isn't just about soldier count, but also their original position. How can we efficiently rank and retrieve these rows? Given a matrix where each row consists of ones, soldiers, followed by zeros, and an integer k, we need to return the indices of the k weakest rows. A row is weaker if it has fewer soldiers. If two rows have the same number of soldiers, the one with the smaller index is considered weaker. The output should be sorted from weakest to strongest. A straightforward approach involves iterating through each row, counting the soldiers by traversing until we hit a 0 or the end of the row. We then store each row's soldier count along with its original index. Finally, we sort this list of tuples. The sorting criteria are first by soldier count, then by index for ties. This gives us the weakest rows, from which we take the first k. While simple, counting soldiers in each row takes linear time, leading to an overall time complexity of O(m) times n for counting plus O(m) log m for sorting and O(m) space. The key insight for optimization comes from the structure of the rows. Soldiers, ones, are always followed by zeros. This means each row is sorted. We can use binary search to quickly find the count of soldiers in each row. For a given row, binary search will locate the first 0, or the end of the row, if all elements are 1. The index of this position directly gives us the soldier count. We initialize a left pointer to 0, and a right pointer to the row's length. While left is less than right, we find the middle. If the element at mid is 1, it means we're still in the soldier section, so we try the right half by setting left to mid plus 1. If it's 0, we've found a 0, so we might be at the boundary, and we search the left half by setting right to mid. Once the loop finishes, left will be the count of soldiers. We store this count and the row's original index in a list, just like the brute force, then sort this list based on the same criteria, soldier count then index. Finally, we extract the first k indices. Let's trace with our example matrix. For the first row, 1, 1, 0, 0, 0, binary search finds the first 0 at index 2, so the soldier count is 2. We store 2, 0. For the second row, 1, 1, 1, 1, 0, binary search identifies 4 soldiers, so we add 4, 1. The third row, 1, 0, 0, 0, 0, has 1 soldier, resulting in 1, 2. The fourth row, 1, 1, 0, 0, 0, also has 2 soldiers, so 2, 3. And the final row, 1, 1, 1, 1, 1, has 5 soldiers, giving us 5, 4. After processing all rows, our list of tuples is ready to be sorted. Sorting by count then index will order them as 1, 2, 2, 0, 2, 3, 4, 1, 5, 4. If k is 3, we take the first 3 elements from our sorted list. The resulting indices are 2, 0, and 3. This array correctly represents the k weakest rows, ordered from weakest to strongest according to the problem's criteria. You'll spot this pattern whenever you have a matrix or array where rows or columns are inherently sorted or have a distinct boundary, like ones followed by zeros. This immediately signals an opportunity to use binary search for efficient element counting or boundary finding, rather than linear scans. The time complexity is O(m) log n for counting soldiers using binary search across m rows, plus O(m) log m for sorting the m rows. Space complexity is O(m) to store the row counts and indices. Mastering binary search in sorted structures is a game changer. Try the next problem to reinforce this pattern. Don't forget to like and subscribe for more efficient algorithm breakdowns.